Hello and welcome back. In this video we discuss about an important concept in fluid dynamics, the Bernoulli principle. This equation is a result of a simplified analysis of motion of a fluid particle using Newton's second law. Consider steady flow of a fluid. For example, air is flowing steadily around a cylinder, as shown in figure. Motion of fluid particles can be better described by the streamline patterns indicated. The velocity of a particle at a given location will be tangential to the streamline passing through that location. Consider motion of a fluid element along a streamline. Various forces acting on the element will be the net pressure and net viscous force from the surrounding and due to the gravity. Assume the flow to be inviscid. That means forces on this element due to shear stress can be neglected in comparison to forces offered by pressure and gravity. Before analyzing motion of a fluid particle, let us review basics of particle mechanics as described by Newton's second law. When a net force applied, a particle of mass m moves with an acceleration a. We know the relation, F equals ma, or F equals mdv by dt. Imagine that the particle is moving from rest through a distance, x, and reaches velocity, v, by the application of this force. Equation 2 can be used to find the work done by the force. We can see that the work done is equal to the change in kinetic energy of the body. A similar work energy analysis of a freely falling body reveals that mechanical energy is conserved when a particle is moving under a conservative force field like gravity. For example, when the body is at a height h, the potential energy is mgh. When it falls to a height x, potential energy decreases and kinetic energy increases, and the sum of these two will be conserved. With this background, mechanical energy conservation of a fluid particle in a steady, inviscid flow will be discussed next. Consider a fluid particle moving along a streamline as shown in figure. The flow is steady and inviscid. Forces due to pressure and gravity are only considered in the analysis. Applying Newton's second law, we can derive an equation balancing the force terms on the left, and ma term on the right, as shown in figure. If the gravity and density remains constant along the streamline, the above equation 1 can be simplified and integrated along the streamline as equation 2. The equation 2 is called Bernoulli equation. It represents conservation of mechanical energy of fluid particle moving along a streamline. Recall that this equation is valid based on a number of assumptions we have made. The flow is steady, inviscid, incompressible, and it is valid only along a streamline. Physically, each term in equation 2 represents various energy terms. The physical meaning of this equation is that sum of flow work, kinetic energy and potential energy per unit volume of fluid is constant along the streamline. In summary, this equation stands for conservation of mechanical energy for a steady, inviscid flow along a streamline. Consider steady flow of air along a streamline from point 1 to point 2. The velocity of air at location 1 is 10 meter per second. Elevation of location 1 from reference axis is 9 meter. Location 2 is 10 meter above the reference. Pressure at location 1 is 50 Pascal and at 2 is 10 Pascal. Calculate the velocity at location 2. We can use Bernoulli equation for solving velocity v since mechanical energy is conserved. Total energy at 1 will be same as at 2. We can solve the unknown from this equation. The velocity at 2 can be calculated as 12.6 meter per second. Consider another example. Water is flowing through a hole at the bottom of a large tank filled with water. Tank is open to atmosphere. The level of water in the tank is 10 meter. Calculate velocity of flow. Assume steady flow and neglect viscous effects. We can imagine a streamline in this flow and consider two locations in this streamline, one on the upper water surface and the other just at the hole exit. Since the tank is open to the atmosphere and water flows out to the atmosphere, the pressure at these two locations will be atmospheric pressure. Since this is a large tank, water level falls very slowly. Therefore velocity at location 1 can be neglected. Now, we have Z1 equals 10 meter and Z2 equals 0. Using conservation of mechanical energy derived using Bernoulli equation, we can find the unknown velocity. Consider a wing of an aeroplane. These structures have specially designed aerodynamic shapes as shown in figure. Possible streamline patterns are indicated when such an aerofoil structure is kept in a steadily moving stream of air. Now consider the aeroplane flying at a speed of 500 miles per hour in standard atmosphere. Velocity of air at some location on the surface of the wing is measured as 600 miles per hour. Calculate the pressure at this location. We will solve this problem in class. Finally, the summary of this video is the Bernoulli equation. This represents conservation of mechanical energy for a steady, inviscid, incompressible flow along a streamline. Hope you understand the Bernoulli equation.